Okay, so let's talk about, hold on, let me put this on first. Okay, so let's talk about bond order and the bond lengths. The concept of bond order is a pretty simple concept. It's basically referring to the multiplicity of the bond, right? So, for example, if you have a single bond, the bond order is one. If it's a double bond, the bond order is two, and so on and so forth. So that's, nothing too complicated about that. The bond length is the distance between the nuclei of the two atoms joined by a covalent bond. And it turns out that the bond length is affected by several factors, not the least of which is the nature of the atoms involved in the bonding and the bond order. All right, so some examples are shown here. So the hydrogen to hydrogen bond length is 74 picometers, for oxygen is 121 picometers, and you see values given for other atoms. All right, now the bond energy is related to the bond order and the bond length, and by definition, it is the energy required to break 1 mole of a particular type of covalent bond in a gas phase compound. All right, so if you have, for example, a hydrogen to hydrogen bond, then it takes 436 kilojoules to break it up to form the atoms. In the case of water, if you want to break the hydrogen to oxygen bond, it takes 499 kilojoules to do so. And then for the remaining species, if you want to break that bond, it takes this much energy to do so. All right. Now, in the case of the hydrogen to hydrogen bond, that value is precisely known. No problem in terms of determining that value. However, for the oxygen to hydrogen bond, as you can see, it depends on the nature of the compound itself, because the energy required to break one bond here is not the same as the energy required to break the second bond here. All right. So because of those differences, um, in terms of the energies, as they differ from compound to compound, what we do is use an average bond energy to give us an idea as to how strong a typical bond, for example, OH, is what it is. Okay, so that gives us this table right here. So this table is um, a table giving you different types of bonds and their corresponding bond lengths and their bond energies. And if you look at this table, you see that there are certain trends that will become apparent. So one trend I want to talk about is how the bond lengths and the bond energy is affected by the multiplicity of the bonds. So for example, if you take the carbon to carbon single bond here, you see that the bond length is 154, but when you move on to the carbon to carbon double bond, it decreases to 134. And when you look at the carbon to carbon triple bond, it decreases further to 120 picometers. So one can clearly see the trend, whereas the multiplicity of the bond increases, the bond length decreases. And correspondingly, the bond energy increases, right? So you see it increases from 347 in the case of the carbon to carbon single bond. And then when you get to the carbon to carbon triple bond, it gets to 837. So the bond length decreasing correspond to an increase in bond dissociation energies. All right. You can also see if you take these first four on this side here, you can see that the bond length is dependent on the size of the atom. So if you compare these four, hydrogen to hydrogen, hydrogen to carbon, hydrogen to nitrogen, and hydrogen to oxygen, all right, you'll notice that the hydrogen is remaining constant here, but we're varying the different elements here, hydrogen, carbon, nitrogen, and oxygen, all right? So what do we notice? Well, we notice that the bond length varies according to the size of the changing atom, all right? So hydrogen is the smallest of these three, followed by oxygen, followed by nitrogen, followed by carbon, right? And you'll see that there's a corresponding decrease in the bond length, right? So the bond length here, in the case of this one, is 74. And then in the case of oxygen, it's 97. And then in the case of nitrogen to hydrogen is 100. And then in the case of this one, it's 110. So basically, if one atom is held fixed and you vary the other atom, the bond length is dependent on the size. The greater the atom in terms of size, the greater the bond length. And there's a corresponding change in bond dissociation energies as well, as you can see over here. Then what else? You can see it also, that trend that I described, you can see that being true also for diatomic molecules, such as fluorine, chlorine, bromine, and iodine, right? As you go down the group, right, from fluorine to iodine, the atomic size increases. So you see that the bond length increases as well, okay? And you see that there's a corresponding decrease in the bond dissociation energies, all right? So those are some trends that you'll observe when it comes to looking at the variation of bond lengths and bond energies compared to other factors such as the size of the atom and the multiplicity of the bonds. Okay, so this is just a summary of what I just mentioned. The higher the order, the shorter and stronger in terms of the energy of the bond. A nitrogen to nitrogen double bond is shorter and stronger than a nitrogen to nitrogen single bond, all right? And the reason for that, of course, it's a purely electrostatic variation. If you have more electrons being shared between two atoms, then there'll be a stronger electrostatic attraction between the respective nuclei and the shared electrons, and therefore the bond will be shorter and stronger. Okay, so the table that I just showed you can be used to calculate the energy or enthalpy of formation of different substances and also the enthalpy of certain reactions. But I must say this, that you have to be careful in terms of using these values because there are some limitations. The values that you see in the table, let me go back to this table here. The value that you see in this table here only applies to gaseous compounds, right? So if the compounds are in a liquid state, solid state, or aqueous state, then there will be significant deviations of the enthalpy changes calculated based on these values compared to what the actual values are. So that's one limitation of the use of these bond dissociation energies. But they're useful for gaseous reactions. And they're useful also for the, well, let me just stick to gaseous reactions, right? They're useful for calculating the enthalpy of gaseous reactions. So this question that you see here is asking for you to use the tables on the bond dissociation energies from the tables given to calculate the enthalpy of formation of this compound known as hydrazine. Okay, so basically, this is the equation for the formation of hydrazine from its elements. So using the bond dissociation energies, you're supposed to calculate the enthalpy change of this reaction. So the way we do that is, right, we have to basically determine what the Lewis structures of the different molecules are. So these are the Lewis structures of the two hydrogens. This is the Lewis structure of the nitrogen. And then we have the Lewis structure of the hydrazine over here, right? So when we consult the table, we see that the bond dissociation energies of hydrogen is 436 here and here, and the bond dissociation energy of the nitrogen is 946 kilojoules. And then over here, for nitrogen to nitrogen single bond, the bond dissociation energy is 163. In the case of the nitrogen to hydrogen bonds, the bond dissociation energy is 389. So, how do we use these values to calculate the enthalpy change of this reaction? Well, this is the way we're looking at it. Basically, we're assuming that all these bonds are broken to form the separate atoms, as you can see here, and then the bonds are formed to end up with your product, right? Now, in order for bonds to be broken, energy would have to be expended, right? You'd have to actually use energy to break up the bonds between the nitrogens here and the hydrogens here. On the other hand, when bonds are formed, energy would be lost, right? So therefore, the bond dissociation energies that you would use for the bonds and the products would be expressed as negative values, all right? So that's why you have negative 389 here for the N to H bonds and negative 163 here for the nitrogen to nitrogen bonds. So this is the way we would set up the calculation. Basically, what you'd have to do is add up all the energy that is required to break the bonds and subtract from that all the bond dissociation energies that you'd find in the product, right? Which, of course, is tantamount to adding up all these negative values. So as you can see here, it's 946 plus the 2 times 436 kilojoules. That's basically the total amount of energy required by the reactants. So that's what we have here, 946 plus 2 times 436 kilojoules. And then as far as the product is concerned, we express the sum of these bond dissociation energies as negative values. So it's 163 kilojoules plus 404 times 389 kilojoules. And that would be representing the amount of energy that is negative. So that's why we express it as a negative value here and here, right? So let me just do this math here on my calculator. So 946 plus 2 times 436 minus 163 plus 4 times minus 389. And according to my calculations, this works out to give you a final answer of, okay, 99 kilojoules. Okay, where should I put that here? 99 kilojoules. And that would be the answer to this question. All right? Okay, so that's basically it for this chapter. And the next chapter will be chapter 10, which deals with three-dimensional structures of molecules and ions and so on. Okay, until next time.